Kubernetes for Humans.
Hello, everyone, and welcome to another episode of the Kubernetes for Humans podcast. Today, with me in the show, we have Ricardo. Ricardo, do you mind introducing yourself?
Hello, thanks for the invitation. It's a pleasure to participate. My name is Ricardo. I'm a computer engineer at CERN. I lead the platform infrastructure teams in CERN IT department. I've been at CERN for a long time. I've worked a little bit on many things, from the great times almost 20 years ago as a student to then working on storage systems, computing systems, monitoring systems. And apart from a little break from CERN, then I came back to work on cloud computing, and I've been quite involved in cloud native, Kubernetes, and also the Cloud Native Computing Foundation. I'm a member of what's called the Technical Oversight Committee and the End User Technical Advisory Board. So I help out a bit in the community and try to give as much as we can from CERN to the community as well.
So, super rich and interesting background. Maybe let's do it like chronological. Like let's start and then let's continue from there. What led you to computer science? Like, how did you start? What were your first jobs, and how did you end up in like a CERN for? How do I pronounce it right? Like it's like
CERN.
CERN.
Yeah, CERN. Yeah.
So, so what led you to there? So if you can a bit on the your origin story, if you will.
Yeah, absolutely. So, I've always been around computers a little bit. My dad gave me one. That's probably the first mistake when I was quite young. Back in the days, it was quite painful actually to work with computers, but I think I always took the challenge a bit, and I was quite entertained into trying to understand and going through the pains of computing at the time. So this led me to a couple of like summer jobs, programming here and there, helping out in a couple of companies of people I knew, and then eventually taking computer engineering in university. And then the transition to CERN was actually from the university. So I had a professor that was collaborating with one of the experiments here at CERN called Atlas, one of the two main experiments that were looking for the Higgs boson a few years ago. And from there, we started a small effort inside the university to create a cluster to help out and donate some computing to CERN. A very small effort at the time. But I also found out there was a possibility to do internships here at CERN as students. And this is it. I then contacted and sent my application. And I ended up doing my master thesis already here at CERN. So that was
And
my
you never
path.
left. And you say that you never left.
I never left. I did take a sabbatical for 2 years to try something. I wanted to try a bit industry as well. So I did take 2 years from CERN, and then I eventually came back.
Okay, no, that's super cool. I think that we're like saying CERN quite a lot. I know the place, but I'll be happy if you can, explain to like all of the listeners what is it, where is it, why is it important, and if
Yeah.
you can share some like general background for our listeners.
Absolutely. Yeah. So CERN, we got into the big news just before 2012 and the discovery of the Higgs boson. But CERN exists for 70 years now. We celebrated 70 years last year. So it's the European Laboratory for Particle Physics, and what we do is large experiments around fundamental research, and in particular for particle physics. So we try to see the very, very small by having these quite large experiments like hosted here. So the mission of the facility is to do fundamental research. And the big experiment that we have right now is called the Large Hadron Collider, which is a particle accelerator. It's 27 kilometers in perimeter. It's 100 meters underground. And we circulate beams of protons in two different senses, clockwise and counterclockwise. and we accelerate them to very close to the speed of light, very high energies, and at specific points we make them collide. We smash them against each other in particular points where we've built these quite large experiments. And these experiments act like big cameras that help us try to see what happened in these collisions. And what we try to understand is basically the nature of matter and the nature of the universe. So some of the experiments are centered on discovering new particles, like the Higgs boson. Others, like the Alice experiment, actually tries to understand the nature of matter and how it looked right after the Big Bang in something that's called quark-gluon plasma. It's a very interesting experiment as well. Apart from that, there's a ton of other things going on here. So right next to my office here is what we call the antimatter factory, where they actually create antimatter and try to understand it as well.
Now
So
that sounds
yeah.
cool. Like that sounds super cool. So, first of all, again, like very unique and not like most of our like previous guests so far. But explain to me, like you're a computer science guy, right? Like I am as
Mhm.
well. Most of what you're describing sounds a bit more like, physics, right? Or maybe
Mhm.
like typical like engineering. And you were there for the last 20 years. So maybe if you can share a bit like where is the software in all of it?
Yeah, absolutely. So in reality, when we do these collisions that happen billions of times per second in the different experiments, what is being generated is these detectors are acting like gigantic cameras in practice. And they are taking something like 40 million pictures a second. That's the rate where we are looking at things. The result of this in reality is just data. And like if we count the experiments, the large ones, they will generate something like 1 petabyte of data per second, which obviously we cannot store and analyze. So what we do is we have what we call online systems that filter this data, and this is done on the nanosecond level. So this is already, in many cases, custom hardware. In other cases, already done by software in things like FPGAs. And then we have additional filters that bring the data rates down to a few tens of gigabytes per second. And this is what we store here in our storage systems, here in 2 data centers on premises.
Mhm.
And then once we have that stored, we have to do what we call reconstruction, which is to try to see from this raw data what actually happened in these collisions. And we reconstruct the events. And for this, we need a large amount of computing capacity. So on premises, we have something like 500,000 CPU cores. If we count the project that I actually came to help out with, which is this worldwide computing grid, where we connect 200 different sites across the world together, we
Mhm.
offer over 1 million CPU cores today. And this is where we need the software for the systems that maintain all this infrastructure. But then, of course, a lot more software even to actually analyze all this data and even for the event filters. And we also have a lot of simulation data that help us design and calibrate also these instruments. So it's all about, it's always been like this at CERN. It's always about pushing a bit the boundaries of technology, both from a hardware and a software point of view.
No, that's again like sounds very interesting and unique. So it's like real big data, right? Like in the end of the day, you're saying there is the problem of collecting the data, like you're running the experiment, but then how can I make sure that how can I monitor the results or get the results basically given this like vast amount of information? And after you already have all of those data in your like on-prem database, the data storage, right?
Uh-huh.
And you need to analyze it. And you're saying that in order to analyze such vast amount of data, you need a lot of unique, like maybe both software and hardware, right?
Yeah, absolutely. So we collect around 100 petabytes of new data every year. So we've accumulated over 1 exabyte since the LHC has been running. So then all this storage is already quite a challenge, but then we have to distribute it to the computer centers that have the computing capacity. And then we need all the capacity to actually reconstruct the events and then give to the physicists the data in the formats they need to perform their analysis.
Okay. Okay. That sounds very interesting. So, I must ask, as the title of the podcast is Kubernetes for Humans, right? So where is Kubernetes? Like, where is it? You also mentioned like the CNCF and different SIGs that, I'll be honest, I didn't really knew. So if you can share a bit about, first of all, your background with Kubernetes, when did you guys start using Kubernetes, and then maybe a bit more about the broader ecosystem of Kubernetes for computing like models.
Absolutely. So, my personal experience comes from containers. When I took some time off from CERN, I was working in New Zealand for a public cloud to set up a public cloud infrastructure in New Zealand. And this was mostly virtualization, but we started looking already at containerization as well and seeing what we could offer. So when I came to CERN, back to CERN, I joined the cloud team, but I was really willing to start looking into containerization. And at the time, if you remember, it was around 2015. It
Mm-hmm.
wasn't even sure that Kubernetes would be the winner. This
Yeah,
would be
yeah.
the early days. So Docker was very well established, but people were talking about LXC also for containers. And then if you looked at orchestration, there was Mesos that was very present,
Mm-hmm.
Docker Swarm, and Kubernetes. So what we did was we started offering our users internally a way to orchestrate clusters in any of these systems. So they could decide if they want Mesos, if they want Swarm, if they want Kubernetes. But things moved pretty fast, and it became quite clear where the momentum was going. So basically, I started going to KubeCon. I think the first one I attended was in 2017 in Berlin.
Mm-hmm.
And I started meeting the community. We had some pretty unique scaling challenges. So we started interacting with SIG scalability as well to try to fix some of those. So this is where we also we had some experience collaborating with open source communities, but we saw that here there was particularly a good momentum to get things done, and we saw the potential for our next generation of our infrastructure. So this led to us basically being very present on presenting our use cases at KubeCon in different sessions, making case studies, contacting other end users. So it kind of made CERN quite popular in this cloud native community. So we joined the CNCF as end user members as well. And then we started by offering services like traditionally IT service, more like business computing kind of thing internally using Kubernetes. But the scientific computing use case was always there. And this is what we were pushing for. It took a couple of iterations to get all the things we needed to scale out, both on management of containers, but also scalability of Kubernetes, large clusters, things like this. So it took a while, but you asked about where is it used? I would say it's used everywhere. So business computing is kind of very well established. Scientific computing, we have the machine learning platforms internally. They run on Kubernetes. But the most exciting ones, I think, are the really critical things, which we call online, which is the systems that control the detectors and run the filters. So for example, for Atlas, for Run 4, which is the new upgrade we'll do in the next couple of years, it will be a gigantic Kubernetes cluster underground next to the detector. Alice and CMS are looking at doing the same. And even the control systems for the accelerator in the next couple of years will be fully managed by Kubernetes. And this means like controlling the beam. So the real core of the business will be in Kubernetes.
No, that sounds like a huge adoption. Maybe you can share a bit. I'll be honest here. Like, I never worked at like the public sector. Like all of my life, I worked in the industry, and like you measure things by money, right? Like, in the end of the day,
Mhm.
company wants to like earn money, and then it uses Kubernetes, and you have someone that guides the process. It can be a CTO, it can be architect, or whatever. And like, it's always a trade-off, right? Should we build it? Should we buy it? Like, there's a lot of different like trade-off
Mhm.
where you're trying to understand. Walk me through, like, how does it work for you guys? Like, who calls the shot? Like, in the end of the day, it sounds that Kubernetes is now super adopted, but
Yeah.
I must guess that it costs you a lot of labor to make it happen, right? and because your use case is quite unique, then why should you contribute to the CNCF, right? Like, why to do it? So if you can share a bit about the internal of like how things are going in like, yeah.
Yeah, so that's a very good question, and there's no one answer because CERN is actually quite a large place. So the adoption has been gradual in different teams and different departments. So, but like to the reasoning to adopt this kind of technology, you mentioned in the industry, it's not that different internally. I think the
Mhm.
main difference is that we have a fixed budget, and that budget is not going to grow because we're not selling anything.
Mhm.
So our main challenge is always to do a lot more with the same budget, and this is going to happen again in a couple of years where we are increasing the amount of data by 10 times, and we have to be able to store it and analyze it with the budget we have today. So this is not
Mhm.
going to increase, and this really pushes us to investigate new things. We used to trust that technology, the hardware would increase at a rate that suited us with this Moore's law, every 18 months doubling the capacity. This is no
Mhm.
longer the case since a few years, which means we need this kind of paradigm shift, be it in the infrastructure layer, be it in the computing models, like using machine learning platforms. So basically, this is how it goes. If we look at 20 years ago when I joined, we were basically building our own software, our own
Mhm.
infrastructure software middleware, because no one else had big data, or at least they were not collaborating.
Mhm.
Today, this is no longer the case. We don't have to build our storage systems or unnecessary. Actually, storage is a little bit special. We do build our own,
Mhm.
but like the workload management, the networking layer, all of this, we moved into collaborating into these much larger communities with very strong organizations behind them and join those efforts. And internally, what we usually do is we pick up some good use cases that can really benefit from this, and where we can show the benefit, and we get an agreement to do small proof of concept prototypes. Can be 6 months, a year. For example, recently with the accelerator sector, we've done a 1 year effort, and by 1 year we had a couple of production use cases running, which meant we could then go to management and say, this is the path we think people should start looking at. And then you get more resources and you can grow the teams. So I guess it's not that different from the industry. The main difference is that we don't aim to make more money because we don't sell things. We
Mhm.
try to be more efficient with a capped budget.
And and who is like, again, like different organizations take different approach. Like, is it a top down kind of things? Like are you and like, I don't know, like a couple of other guys or girls are sitting together and like deciding what will be the direction for all of like CERN, or is it more like independent like areas? Like, how does it work?
Yeah, so it's more the latter. There
Mhm.
is in some areas there is a top down in some things that are really core, and also when we have strict timelines that we need to comply with,
Mhm.
that are driven by the accelerator. But for this kind of experimentation, yeah, CERN is a quite good place for this kind of thing. You can justify these efforts to experiment with new technologies for a limited time, and then present some nice results, or not so nice in some cases. But it is a very um, technology aware environment. So there's ideas popping from with every team, and we try to put everyone together when there's shared interest. Uh, like for example, this effort we did with one of the experiments with Atlas, already back in the first experiment, I think we started looking at 2017 to replace their online farm with Kubernetes.
Mhm.
This actually resulted in a quite significant success. So yes, the other experiments are looking to do basically the same, just reproducing the same environment in their own caverns. So it comes from individual teams, and then the word spreads and goes up to the management. At some point, when you need the resources, you have to go up and ask for it.
Okay. No, that's interesting. So, you mentioned like you're in a couple of like SIGs, right? Like computing models, I want to say, and like the end user models, or if you can share a bit about like the bigger, like the bigger ecosystem, because in the end of the day, there are other, I guess, right, like universities or labs and so on that might tackle the same problems, right, or similar problems. So
Mhm.
how does it work? Maybe share a bit more about like the broader ecosystem.
You mean with the Cloud Native Foundation?
The Cloud Native Foundation, yeah.
Yeah, sure. So, uh, yeah, the anecdote is always to show this picture of the CNCF landscape with I don't know how many projects it has there now.
Mm-hmm.
It grew to. I think this is one of the main differences from previous efforts like OpenStack is that the stack in the CNCF covers all areas. It's not
Mm-hmm.
just the core of the infrastructure. It goes to databases, goes to storage systems, it goes everywhere, like
Yeah.
platform engineering, you name it, everything is there.
Mm-hmm.
So what the foundation really required, and it was there from the beginning, is what is called a technical oversight committee that oversees the projects. So it's not leading the project or deciding where the project should go, but
Mm-hmm.
it is taking care of the maturity of the projects in a sense of recommending and setting them to different maturity levels. So usually a project will join the CNCF as sandbox, which
Mm-hmm.
is very early phase, maybe building a community, but doesn't have necessarily the required governance in place and vendor neutrality and best practices that will assure that it's sustainable long term. And this is the role of the technical oversight committees to help those projects grow and do some due diligence when they apply to move levels. And the goal is to get them to graduated state, which is these levels are a reassurance for end users to know that what they can expect from a project.
Mm-hmm.
So if you would be, say, a university or in a company and you adopt a graduated project, you know the project has some level of sustainability that makes you quite confident. You probably will still want to do some evaluation internally, but lots of things you can trust. If you're doing the same for Sandbox, then your due diligence should be a lot more extensive, especially if you plan to bet on this for your core business. So this is where the technical oversight committee tries to help the projects and the community. And then recently we created this, it's called End User Technical Advisory Board, which is more an end user perspective to that. And the goal here is to put end users together, but also to understand from the end users how they see the project health. So it's kind of complementing the maturity levels, but also understanding by talking to the end users what are the gaps. So one of the efforts is to establish what's called reference architectures, which is you would just draw your stack, say which projects you use and why you're using it. Maybe you did some comparisons as well. And sometimes what we see is we identify gaps in the full stack that are being fulfilled by commercial products or where there's no project that can
Mm-hmm.
do this item. And then we bring this back to the community, open it up, and maybe someone will have cool ideas and maybe launch a startup or start a project to work on this area. Yep.
No, that's cool. And how many projects are there, like specifically for your guys' use case, like physics, particle monitoring? Like, how big of an ecosystem is it? Yeah.
It is quite large. So there are pieces that are required by everyone. If you have a cloud native stack, like the registry, we use Harbor for a registry. Then we have the Kubernetes clusters. That's already a bunch of them. It's like Containerd, uh, Kubernetes itself, etcd, all the add-ons that we add in the clusters. So things like runtimes, security, we use Falco. For monitoring, we use Prometheus. All of this starts adding. So I would say we can easily use at least 30 of those projects, um, not only for the cluster orchestration, but then the higher level tools like Argo to do your application management with GitOps and many other projects. And we have a recommended stack, but then each individual team will also pick and choose on their particular needs. So yeah,
No, like the amount of like CPUs that you mentioned, like 1 million CPU, is like it is quite a lot, right? Like those are, I'm guessing one of like the biggest clusters in the world. If I would like need to, you know, to benchmark you guys, or very similar to like the biggest project, right? So are you still hitting the same technical limits that Kubernetes have, or are
Yeah.
things matured?
Yeah, so 1 million cores is our total capacity across the whole world. So it doesn't mean that everything
Mm,
is running on Kubernetes. Like
yeah.
one thing that is quite interesting in this particular area is that we had this grid computing infrastructure where we have developed our own software for everything 20 years
Mhm.
ago or 15 years ago in production. But what's been happening is that a lot of these sites have replaced completely the full stack, which is the Kubernetes endpoint. And
Mhm.
this is the proof of like how useful
Mm,
these things are, because it gives us the abstraction of the whole thing. Like it gives us the abstraction to submit workloads, to monitor the workloads,
yeah.
to collect the logs, to do everything. So in many cases, what these institutes and organizations have done is they basically scratch their old infrastructure, deploy the large Kubernetes cluster, and give us the API to submit workloads. And this works quite well. And the same happens internally. This is gradual. Like, so services move from their legacy deployments to Kubernetes gradually. And this has been happening in all areas, in both business and scientific computing. So it's not like a one large cluster. We actually learned quite early in our process to not have very large clusters. And the reason for that was scalability at the start, but also blast radius. We gave a pretty entertaining talk with a colleague 2 years ago where we by mistake started deleting all our clusters during
Mhm.
an operation. We deleted like a third of our capacity. And because we have this, instead of having very large cluster, we have this policy of clusters as cattle to reduce blast radius. We actually didn't have any downtime. We had some service degradation, but by
Mhm.
deleting one third of our capacity, we still stayed up, which is kind of
Yeah,
an
quite
example
impressive.
of, yeah. It was stressful at the day, but it gave for a nice presentation and some lessons learned. So yeah.
Okay, no, that's cool. So we are like closing to the end of our time. Maybe you can share a bit what do you think we have in store for like the Kubernetes ecosystem and for like research institutions and so on. Like what, 1 year, 2 year, 3 years from now, what's going to change? Is Gen AI doing any change by the way? Like, is it something that you guys are, yeah, like
Yeah.
talk away, like what's going to happen?
Absolutely. I love to talk about this part. So the last couple of years we actually been pushing for having Kubernetes, having all these primitives we need for scientific computing. And this means batch primitives like queuing, advanced scheduling, capabilities. And we've been presenting this quite a bit. Uh, I think if you ask me what GenAI has done for us is that it made these features so required for Gen AI that we are getting them finally. So even for more traditional scientific computing, we got this like batch primitives thanks to Gen AI.
Mhm.
But that said, we don't do necessarily a lot of Gen AI for research at CERN right now, but we do a lot of ML, a lot of machine learning. So this is basically our machine learning platforms are Kubernetes from the start,
Mhm.
and this is where a lot of the investment will go, so that we have uh, improved support for accelerators in these clusters, but also that we can do better hybrid deployments and integrate external resources, public cloud resources to expand our capacity and especially access like specialized accelerators, all of this. So I think where we are going is that Kubernetes will have to become even more flexible than what it is in onboarding all these special environments, to put inference in FPGAs underground, to get I don't know some specialized accelerators somewhere in a region, God knows where in the world.
Mhm.
All these things will be essential for scientific computing and for Gen AI, I think.
Okay, that's cool. Any last remarks, Ricardo, that you want to say to our listeners?
Well, it's what I keep repeating is that all this community has been like a huge changer for the way we do computing at CERN, but also
Mm.
it has enabled us to look into the next 10 years and our challenges in a much more confident way. So we always thank everyone And yeah, thanks again for the invitation, and thanks everyone for all the work in all these tools.
Sure, thank you. Like a great and very different episode. So pleasure.